Okay. So we continue now with the talk by Dave Stevenson that will tell us basically how to form Jupiters, how to accrete gas on some big solid core. How we form the core, that will be discussed later on.
Yeah.
Dave.
So after the beautiful purity of celestial mechanics, we're now going to do something that's dirty. The particular problem that I want to talk about is this one. I have a star, and I have a disk of the kind that Ruth talked about, and I embed in that disk an object that is small compared to the scale of the system, although it's a significant mass in terms of planets. Might be, for example, the mass of the Earth. And the question I'm going to attempt to answer is, to what extent does the gas within this disk concentrate around this nucleating seed, and whether there might be some kind of instability that causes the gas to continue to accumulate. So we're dealing with a case where the sphere of influence, the Hill sphere, is small compared to the other dimensions of the system. And just to remind you of what the Hill sphere is, it's the distance from the star times this mass over 3 times the mass of the star to the 1/3 power. And if we're talking about an Earth mass, which is 3 by 10 to the minus 6 relative to the Sun, then inside the bracket we've got 10 to the minus 6, take the cube root 10 to the minus 2. So indeed it is, as I've drawn it here, even smaller than the way I've drawn it. Now, we may eventually get to cases where this local way of thinking about things will break down. But for the moment, I want you to accept the idea that I can consider the behavior of the gas near here, not worry about the fact that the disk is Keplerian, not worry about the fact that maybe at some point the Hill sphere may intersect or at least go to regions of lower density, not worry about rotation, not worry about angular momentum or anything of that kind. And so the problem we're going to consider is going to be simplified still further by ignoring all aspects of the disk structure and just imagining that I've embedded this planet of radius r and mass m, this embryo, which you can think of as a solid body, but it doesn't actually matter. It could be liquid. But it is a lot more dense than the nebula that it resides in. Yes?
This is a Jupiter mass planet?
No. At this point, it might be, for example, the mass of the Earth.
Okay.
But in fact, I'm treating it as a variable, and you'll see how it comes into the calculation. And outside of this high density region, there will be some density of gas. I should have mentioned one other thing. The nebula density here is so low that if I take the mass of gas within the sphere of influence, and multiply by the nebula density, this is going to be much less than the mass I'm interested in. It turns out if you do the numbers that if I'm at Earth masses or something like that, that will always be true. This, of course, is just a statement that I don't have to worry about the self-gravity of the gas before it is perturbed. We're going to perturb it, of course. We're going to clump the gas in, but before it's perturbed, we're not going to have to worry about the self-density of the nebula. So we're interested in this problem of what the density of the gas is as a function of distance away from the surface of the planet. And indeed, it's going to turn out often that I don't have to worry about exactly where the Hill sphere is. This is sort of infinite. Now, you have to be careful in a gravitational problem. You can't really make it infinite. But this is, so in essence, the question I'm now going to ask is, what is the mass of the atmosphere? How am I going to define that? I'm going to define that as the integral from the radius of the body, that is the surface of it, out to the Hill sphere, although often it won't matter exactly what I put for the upper limit. 4 pi r squared times the difference between the actual density at position r minus the nebula density, which I will sometimes write as rho infinity because it will be the density when I go infinitely far away from this body, dr. And the interesting question is going to be, what are the conditions such that this approaches this mass? So that's going to be the question. Now, before I go any further, I'm going to put on this board where I'm headed. And this will be a deliberately provocative set of statements I'll make here, because that will keep your attention. It will make you realize that where I'm headed is something interesting. So I'm going to be provocative by making a list of what I think are, in some sense, wrong ideas.
Dave?
Yeah?
Don't you have to take into account the body radius as well? Is an alpha bound?
The Bondi radius will come into it. You will see it emerging naturally from the calculation. But at this point, don't worry about it. It's actually going to be substantially less than the Hill sphere in most cases. Initially, it will be. So be patient. You'll get the Bondi radius coming out very naturally from the calculation. So here are some wrong ideas, what I think are wrong ideas. And we will come back to this list later after I've done my analysis. So wrong idea number one is that there exists a well-defined critical mass, that is this core, well-defined critical M, to make a giant planet. I'm going to try and convince you that although calculations will give you some number, that you need to be very, very careful in interpreting that number, because it's not really a number. It's a function of many things, and we have to understand that function. And the fact that the literature is filled with calculations that give a number like 10 Earth masses doesn't mean you should believe 10 Earth masses. Statement number two is that giant planets form at large A. This is a very commonly stated statement, and I'm going to explain the reasons why this might not actually be so. There are historical reasons for why people think this, and there are reasons related to our solar system, but the question is whether that's generally true. Statement number three, that in order to collect, and here I'm not just talking about giant planets anymore, I'm talking about the puffy bodies that we've seen in the TTV, which have substantial atmospheres extending out to 2, 3 Earth radii, but the mass is only a few Earth masses. Statement number three is you need to make a body that has a substantial hydrogen and helium atmosphere quickly. Now, quickly means of order a couple of million years. Like, 2 or 3 million years. And this, of course, is a number you've heard already from others. This is the number that characterizes the time scale on which the nebula is removed. And, of course, this whole analysis I'm interested in here is concerned with the case where the nebula is there. But the question is, what if I remove the nebula slowly? If I have an exponential decay of the nebula, can I still do my story here of collecting gas when the nebula is only 1% of what it started with, rather than 100%? Okay, now I'm going to cover up that part, but we will come back to this list. So this is here to provoke you, or at least make you realize that what I'm dealing with in my talk is something of importance.
It also gives an answer to the algorithm Scott was looking for.
Say that again?
It also gives an answer to the algorithm Scott was
Yeah.
looking for with the book.
Yeah. Okay. Now, I'm going to consider 3 different models. And to make it clear what I'm doing in this talk until I get near the end, I'm going to do things that in some sense are not realistic, but they're pedagogically useful. So we're going to go through some exercises that are not intended to be the wonderful numerical models that people go and make, but to elucidate the basic principles. And so the three models I'm going to consider are, number one, isothermal, meaning that the gas is everywhere at the same temperature, even as it clumps up onto the body here. Number two, the opposite extreme, adiabatic, meaning that any clump of gas that undergoes compression through the action of gravity doesn't lose heat. It heats up because of that compression and doesn't lose that heat. And number three, in some sense, realistic. And I'll explain what I mean by these quotation marks when I get to that model. So away we go. Number one, isothermal. With the isothermal model, what we are considering is the solution to this equation. P by dr equals minus rho g. And P, of course, is rho c squared, where c is the isothermal sound speed, and it's a constant. And very importantly, I'm going to go to the limit where I can assume, at least for the moment, that this comes entirely from the embryo, the seed. And so it'll be gm upon r squared. Now we're going to break that a little bit as time goes on, but for the moment let's just think about that case. Then of course this is a simple equation to solve. You know that you've got c squared d rho by dr equals minus rho gm upon r squared. And you can see what's happening here. I've got a d rho upon rho, which integrated gives me log of rho. And over here, I've got an integral gm upon r. And so the solution is going to be in the form of an exponential of gm over rc squared. And I can then just write the solution as rho of r equals rho at infinity, or rho of the nebula, exponential of gm upon rc squared, provided I'm in the condition where, of course, the variation in density because of this solution brings the density down to a value that's very low once I get out to the Hill sphere. And in practice, that'll be true for the numbers I want to use for m, which are something like the mass of the Earth. Now, this is, of course, just the ratio of the Bondi radius to radius. And, of course, this says that the surface density, the density at the surface of the body, is, and I'm going to write it this way, e to the power of a times the nebula density, where a is a dimensionless number, which is gm over capital R c squared. Now, you may recall that this number can easily be large, really large. Okay, so gm upon r is, of course, just the square of the orbital velocity at the surface of the body. So in the case of the Earth, gm upon r is like 7 kilometers per second all squared. That's 50. C squared can be something like 1 kilometer squared per second squared, or 2. So this can easily be 20, 30, 40, 50, and it's in an exponential. So what that means is that when you plot the density as a function of radius, and of course starting only at capital R, what that means is that if A is much greater than 1, which is the interesting case, the density drops really fast, and the characteristic distance over which it drops, this distance here, is of course like r upon a, because if you think about it, in order to change this function by e, that is make it smaller, I'm going to have to change little r from capital R to capital R plus r upon h. So this is the characteristic distance. And so that means that there's a very simple formula that you can write down for the mass of the atmosphere. And I can scale it, of course, to the mass of the embryo. And what am I going to get? So the mass of the atmosphere, therefore, is 4 pi r squared times the thickness of the layer in which the density is dropping a lot, which is r upon a, times the density of the nebula times e to the power of a. And of course, the mass of the planet is 4/3 pi r cubed times the density, the mean density of the planet. I say planet, I mean embryo, same thing. So you can see what this is going to be. This is just 3 times the density of the nebula over the mean density of the solid body times e to the power of a upon a. And of course, now you can see the point. This is really, really, really small. It's a tiny number. It can be 10 to the minus 10 easily. I'll give you an example. This can be really, really, really large. But clearly there will be some a for which this approaches the mass of the planet. And so let's look at some numbers just to get a sense of that. So let's take as an example m equals the mass of the Earth, r equals the radius of the Earth. And so that means that gm upon r is about 50 kilometers squared per second squared, 7 kilometers per second roughly. Orbital velocity at the surface of the Earth squared is about 50. And I'll take c squared, this is for hydrogen, at about 500 Kelvin. That turns out to be about 2 kilometers squared per second squared. So in this particular example, A is about 25. And e to the power 25, as you all know, is a big number. So what about the density of the nebula? Ruth gave you a model, the minimum mass solar nebula, and at 1 AU, I don't have to do this at 1 AU, I do it anywhere I like, but just for this example, she had a surface density of 1,700 grams per centimeter squared. This is going to be spread out over twice the scale height of the disk, so in order to convert this into a density, you divide by twice the scale height, and that will give you at 1 AU a density of about 10 to the minus 10 grams per centimeter cubed. So that's going to be our nebula density. This is just an example. Don't worry too much about the numbers, because you'll notice these numbers are going many orders of magnitude. So you don't need to do this very precisely to get the basic idea. And so in that particular case, rho bar over over 3 times the nebula density. Sorry. Well, actually, I can do it. Yeah, I can do the invert. It doesn't matter. 3 times the nebula density. Times with the factor of A in here. If you work that out, it's something like 10 to the power of 8. And if you work out e to the power of A for this number, it's also about 10 to the power of 8. So again, don't worry about the details. Details are not the issue at this point. The message is that when you get to a mass of about 1 Earth mass, and this is just a coincidence for these kinds of numbers, obviously it depends quite a bit on where you choose to do the calculation. In the isothermal case, it really does matter what the temperature of the nebula is. A lot of the other stuff, it doesn't matter much. It's only logarithmically sensitive on the nebular density. But anyway, at about 1 Earth mass, I can already collect around this planet an envelope that is approaching the mass of the embryo. Now, you can and should object at this point that, of course, the calculation's breaking down, but that's not my point. My point is that unavoidably you're going to approach that. If you think through what's going to happen when I do the calculation more carefully, of course, what I assumed here is that it's just the mass of the embryo. Once I start augmenting this by the atmosphere, it gets even worse. And so what that ends up meaning is that if I plot, and this part I can't do analytically for you, but it's easy to do it numerically. If I plot the total mass, which is m plus m atmosphere, as a function of the mass, then of course what's happening at low masses is that it's essentially a one-to-one line, but then as the atmosphere builds up, and of course this happens rather quickly, you get a divergence, okay? The total mass will be larger, so this is a one-to-one line here. But as I add on the atmospheric mass, total mass will start to do this, and actually it'll turn over. So there is in fact, so to speak, a critical mass here, which is defined essentially by requiring that this be about unity. Detailed calculation will give you slightly different numbers, but again, I don't care about the actual numbers, I only care about the concept. So the concept I'm getting across here is that if you had an isothermal envelope, then typically, as you approach of order 1 Earth mass, you're going to accumulate around that envelope an amount of gas that is similar to the embryo. And I will get back later to the question of what actually happens here, which is a concept of criticality in some sense. Now, at this point, if you're thinking about the physics of it, you will be saying, and you should be saying, why the hell am I assuming isothermal? Well, of course, I'm assuming that because it makes the calculation easy. But it's not good physics, because think about what's happening. Unless I can wait a very, very, very long time, it will usually be the case that the heat that is generated by the gravitational accumulation of gas onto this embryo will not be able to escape fully, and so it won't be isothermal. Indeed, there will be some time scale. This calculation is essentially correct if you could wait a really, really long time. Let's have an estimate now of the amount of time you might have to wait. And this is just a rough calculation so that you can get a feeling for the thermal part of the problem. So now what I'm going to do in this simple calculation is I'm going to ask the following question. In time tau, if this thing is radiating at temperature T, to get rid of the heat that is emplaced by gravitational attraction of the gas, what will T be if the total energy that's radiated in time tau is the gravitational energy of formation if I make a mass m of radius r? So I have my gravitational energy, which is avoided g m squared upon r. And because I'm thinking of the case where the atmosphere is becoming comparable to the mass of the core, it's not important for this calculation to worry about where I'm talking about the atmosphere of the core. And what I'm going to do is I'm going to equate that to the best case, which is black body radiation. So I'm going to assume, and of course the atmosphere is thin, remember. And by the way, it gets very dense according to this calculation, so you even worry about the ideal gas limit. But let's not concern ourselves about that for the moment. So we take 4 pi r squared, or some slightly larger radius, sigma t to the 4th times tau. This is a very simple calculation. And if you solve that equation, what you find is that T is 1,000 Kelvin if the time scale is 3 million years. However, it's got a weak time dependence. And the radius comes in as the 3/4 power. This is radius of the Earth. And you can see why that is, because m squared here is r to the 6th, so you've got r to the 5th, r squared, so you've got r cubed overall, and then you take the 1/4 power. So what does that tell us? That tells us that if you were to try to make a planet like this, and you were using numbers like this, it wouldn't work. There's just no way that you're going to get rid of the energy that comes from the accumulation of this atmosphere. And so the isothermal model is indeed unphysical. But it still gives you a feeling for the magnitude of the problem we're dealing with. Boris?
Shouldn't the temperature be inversely proportional to tau?
You're right. Thank you. Yeah. Was there another question? Yes.
Yeah. I remember in Bruce's lecture, it says it would be sigma to the 4th times tau in the optically thin case. But now here you
But I'm not trying to do that. I'm just trying to matching the energy to the this is not a statement about where the temperature is. It's just the only purpose of this calculation is to say that if you try and build it in a few million years, you must get a substantial temperature. This is a different tau.
Oh,
This is a time scale. Sorry. Yeah, I will also have a tau later that's... yeah, I'm sorry. I misunderstood your point. Okay. So much for the isothermal case.
So the units for time here are years, though? Or
Sorry?
the units for time here are years?
Yes. I chose a number that people are interested in, 3 million, to scale it, but it just so happens it comes out to be 1,000. Okay, having disposed of one unphysical case, let's do another unphysical case, but it'll give you a very different answer, and so that will help you understand the character of this problem. So, now we do the adiabatic case. And this one has some technical issues, which I don't want to dwell on because it's not a physically realistic one, but I'll take it far enough so that you can see why it's so different. So in the adiabatic case, we're still, of course, solving dp by dr equals minus rho g, and we're still going to assume that g comes from the core. But now, of course, we have a different equation of state. We're going to assume that the pressure increases as the density increases in accordance with some adiabatic index, gamma. So this is the pressure that you would have if you were just in the nebula, and this is the increase in pressure that arises through adiabatic compression. And gamma, just to remind you, is 7/5 for molecular hydrogen. It's a little bit more for a hydrogen-helium mixture, but for simplicity, I'm going to go with this one because it gives some nice, clean results. Okay, so you can see what's going to happen here. I mean, let's not write down all the constants, but what we're going to have is a d by dr of rho to the gamma. We're going to have a rho over here and a gm upon r squared. And you can see, of course, that it's analytically solvable, but because gamma is not 1, we're not going to get logs, we're going to get power laws. And so let me just write down the result. I won't drag you through all the details. Rho upon rho nebula is 1 plus A times R over little r with coefficient in here, which is gamma minus 1 over gamma. And here we have 1 over gamma minus 1. So in the particular case of molecular hydrogen, that becomes 1 plus 2/7 A. And A here is, like we did before, GM upon RC nebula squared. So it's the same A as before. But of course, in some sense, A is changing in the sense that the sound speed is changing, but I'm scaling it to the value in the nebula. Gamma minus 1 is 2/5, so the reciprocal of that is 5/2. Now, I don't want to dwell on it, but I should at this point, for those of you who are trying to think through what's going to happen when I do the calculation, that there is an issue here that is non-trivial, and that is this is only decaying when this thing is big, which it will be in general. This is only decaying like out of the minus 5/2. And when you do the integral for the mass of the atmosphere, which of course involves rho of r 4 pi r squared dr, you can see that actually the outer radius does matter. But let me not dwell on those details. Let me just give you a sense of the numbers. Remember that in the previous calculation, in order to get something interesting, we needed to have the density of the gas near the surface of the embryo be many, many orders of magnitude enhanced, like say 8 orders of magnitude or even more. So let's go with that idea and ask ourselves, what do I need? This, of course, will be 1 at the surface. And so I'm going to want to have rho upon rho nebula be some really large number. So let me give you an example. Suppose I were to choose, it's not going to be obvious why I chose this, but you'll see how it works out. Suppose I were to choose A equals 3,500. Then this thing in the brackets is basically 10 to the power 3, and so this becomes about 10 to the power of 7.5. And then you're in the ballpark, then you have a density at the surface, that's about 10 to the minus 2.5 for the 10 to the minus 10 I used previously. The scale height is huge now. I'm still assuming an ideal gas. The scale height is huge, so when you do the integral for the mass, it's actually a substantial mass. It turns out that these are the kinds of numbers you need so that the envelope, so that the gas that has clumped up adjacent to the core is enhanced by something like this. And of course, this number, again, it depends a bit on where you are in the nebula, but this number corresponds to a critical mass, that is the mass at which the atmosphere and the solid body approach equality, of about 100 Earth masses. Okay, this is a couple of orders of magnitude, roughly, a couple of orders of magnitude larger than before.
The scale height is now equal to the radius of the embryo. The scale height is now equal to the radius.
The scale height, indeed, is huge. So, yes, and that means you don't need as large a number here in order to have a substantial mass there.
What's the temperature at the surface?
And the temperature in this calculation, Morris, you asked an excellent question because I did actually calculate it. In the example I'm giving, 100,000. That is, now you may be astonished by that number, but it's perfectly possible. There's enough energy. There's easily enough energy. The entropy of the solar nebula, of course, is huge because the density is low. And if I insist on keeping the same entropy and just compressing the material, then I can get high temperatures. And there is enough energy in the gravitational energy of formation because I've got 100 Earth masses. Remember what I told you back in my introductory lecture. Different specific heat, admittedly, but in the case of the Earth, which is 1 Earth mass, I can make 40,000 degrees Kelvin. There's lots and lots and lots of energy in gravitational energy. So it's not that hard actually to make temperatures like this. And when you form Jupiter, you can get hundreds of thousands in principle.
There's also another way to say, because we saw from the equation above that the scale height has to be equal to the radius of the planet, then it means that the temperature is about the escape velocity, equivalent
Yep.
to the escape velocity from the embryo.
Yeah.
So it has to be, for an Earth-sized core, it has to be this 11 kilometers per second.
Yeah.
For a 10 Earth mass core, then you run.
Yes. Okay. Now, interesting thing about this case, it's equally unrealistic, but here's an interesting aspect of this model. Think about how you might actually do this. This is like making a thermonuclear device. It's going to be a bit bigger than a hydrogen bomb because I've got to make this 100 Earth mass core. But anyway, somehow I've made this 100 Earth mass core and I've introduced it into the gas, or I build it on some time scale, which has to be fairly short because if I don't do it quickly, it's not going to be adiabatic. But you could imagine some scenario where you don't want to do it too quickly because then you'll get shocks. But you do it so it's a reversible adiabat. But of course, if it's a reversible adiabat, what happens when I take the nebula away? The gas goes back. So actually, this is a reversible model. That is, I build the planet, I accumulate the gas around the core, I take the nebula away, but the gas will go back. In other words, it'll just flow back out because if it really is adiabatic, that is to say isentropic, then of course it's reversible. And I bring that up because that's a very important part of thinking about this problem. If it's not adiabatic, that is, if the temperature is lower than on an adiabat as you accumulate the gas, it can't go back out. So if I build a body in the nebula, collect gas around it, but allow energy to radiate, which of course is the way you lower the entropy, as you must, in the gas around the embryo, and then take the nebula away, the gas will stay behind, trapped to that core. So that's how you make a planet that has a trapped atmosphere of this kind. You make it by making the entropy of the captured atmosphere substantially less than the entropy of the nebula. Okay. Now let's do the quote realistic unquote model. If you want to see the details of this one, it's actually a paper I published a long time ago, 1983. So this is the realistic. But it's motivated by what we've done. So having seen these two extreme cases with very different answers, 1 Earth mass, 100 Earth masses, something like that, you say to yourself, well, it's abundantly clear now, having gone through those cases, that I have to worry about how the energy leaves the body as I make it. And therefore I have to worry about timescales, and I have to worry about opacity. And that's where it gets dirty, because the moment you have to worry about opacity, you're in trouble, because opacity is not well known. Of course, they're well known for a particular model, but it's not clear. You go into the supermarket of opacities. Do I pick that one? Or I don't pick that one. What do I think the opacity comes from? Does it come from cloud particles? Does it come from high Z elements, or is it just molecular hydrogen? So that's a problem. So what I'm going to do here is show you the solution, which is beautifully simple and instructive, but still doesn't really describe what actually happens. But it is instructive, and it's the model where the opacity is a constant. It's the same all the time, no matter what. So away we go. And of course, now we have to have another equation. In addition to the equation of hydrostatic equilibrium, and of course, the ideal gas equation, I'm going to have a third equation, which is a thermal equation. Okay, so in this model we have the usual equation of hydrostatic equilibrium, and as usual I'm going to assume that the mass is predominantly that of the core. You can cheat to some extent and say, well, this is really more like the total mass. There are some cases where you can do that. It depends on how the gas is distributed in the envelope. But the formalism I'm going to give you certainly treats this as a constant. And then, of course, we have the equation for radiative transport. And this will bring in the element of time, because if I write down an equation for heat flow, I have to know what the luminosity is, and I can't talk about the luminosity unless I talk about the time scale of the process. But here it is. So let me explain what these things are. Yeah.
Yeah, so here adiabatic could also mean that when gas accretes, it does not lose heat. However, gravitational potential energy may be converted into heat, which cannot be lost. So
That is actually what's happening. In other words, the density is increasing through the action of gravity, and that causes adiabatic heating. But by the way, I'm using the word adiabatic, but I'm well aware that this is actually something that the community should not do, at least not in this case. It's really isentropic, and that's not quite the same thing, of course, because I can have systems that don't lose heat but are irreversible. But in the context I did it, I was treating it as adiabatic, which is also the convective state.
yeah, so does that mean that the specific entropy of the gas
Is constant.
would it increase? I mean, if I take into account of the gravitational
No.
potential energy.
No, I'm assuming that, it's an artificial model, of course, but I'm assuming that in the accumulation of the gas, the specific entropy is kept constant. Work is done on the gas, and that raises the temperature at constant entropy. But I'm not dissipating energy. I'm just storing the energy, increasing the thermal energy at the expense of the gravitational energy. Okay?
Thank you.
Let me explain what these things are. Don't worry about the 4/3. That's a technical detail that has to do with this thing, which is called the Rosalind mean opacity. This is, of course, a very standard formula. This is sigma T to the 4th, so it's the heat flux, energy per unit area per unit time. Rho is the density at that location. L here is the luminosity. Now, in the context of the model I'm going to describe to you, it's treated as a constant. How could that be? One way to think about this, and in fact it's not too different from the way people actually make models for the formation of Jupiter, is to say that my embryo of mass m is growing over a time scale of, say, 1,000,000 years. And the luminosity comes from the gravitational energy that is released when planetesimals plunge down to the core and get added to the core, and the assumption is that all of that energy of the infalling planetesimals goes into luminosity. You don't have to assume that, but were you to do so, then of course the luminosity would be Gm, this is just the mass of the core, remember, dm by dt, over r, where the r now corresponds to that m. So in general, this is a variable. Now this is a quasi-steady state calculation. I'm not going to go through the details of whether that's legitimate, but actually for the timescales I'm going to talk about, it is roughly true. This, of course, is the steady state equation. So L upon 4 pi r squared at position r inside the atmosphere is, of course, just the energy per unit area per unit time. And remember, kappa rho r is dimensionless. So I could also write this as d sigma t to the 4th by d tau, where tau, that's the other tau, the optical depth. Now, the beautiful thing about these two equations is, of course, that I can take their ratio and I get something really simple. Right? Because the rho drops out. I've got a rho in both places. Okay, I've got an r squared in both cases. So I get something spectacularly simple, which is that d sigma t to the fourth by dp is a constant. So just taking the ratio of those two things, d sigma t to the fourth by dp equals a bunch of things that I'm assuming is actually constant. So this turns out to be 16 pi gm over 3 kappa L. Now comes something that is not obviously true, but when you work through the numbers, it's okay, usually, which is I integrate this equation, but assume that the values of temperature and pressure throughout most of the envelope are large compared to the values at the boundary, wherever I set the boundary, in which case it just becomes t to the fourth equals a constant times pressure, where this parameter A is 3 kappa L over 16 pi sigma gm. Or do I have it? No, maybe it's the other way around. Let me look at that for a moment. Do I have that inverted?
Yes. Except that the sigma should be on the bottom. And you're inverted from what your sigma.
You mean this should be to the minus 1 or this? Yeah, this should be the minus 1. So this is actually the right one. Now, but importantly, we have this form, which looks like radiation pressure, but of course it isn't. Okay, this has nothing to do with radiation pressure, but this is a common relationship that you have between temperature and pressure in a system that is delivering heat by radiation. Oh, important point. This is convectively stable. This says that T is proportional to pressure to the 1/4. And adiabat has T proportional to P. If you work it out, it's something like 1/3. Doesn't look like a big difference, but it's actually important when the pressure varies by 10 orders of magnitude.
So the statement you've already made in the previous lecture, that it depends on how kappa is changing.
Yeah.
So this is the case because kappa is constant.
Say that again.
The fact that the difference goes this way, third versus
Yeah.
quarter, depends on the fact that kappa is constant,
Yes.
which is the comment you made.
Yeah. Actually, I made a comment about that, I think, on Monday or sometime. I will get to that. I will have a side brief discussion about opacities. But this is something I find a lot of people actually don't realize. Jupiter, our Jupiter, would not convect if the opacity were constant. Anywhere. Would not convect anywhere. I know this is an astonishing statement, but it's true, because the temperature would always be sort of like this, for different reasons, and not this equation. But the temperature would sort of go as pressure to the 1/4, and that would always be subadiabatic, and so it would not convect. So the reason why Jupiter convects almost everywhere, and Saturn convects, and brown dwarfs convect, etc., is because the opacity is not constant. I know I'm undercutting the value of this calculation, but it's still actually useful. It's still instructive, so I'm still going to continue with it. Okay, now, so I've got T to the fourth scales with pressure, but of course I also have the equation for an ideal gas, which I haven't used yet, right? And so my equation of hydrostatic equilibrium, 1 upon rho dp by dr, is, of course, if P is scaling with T to the fourth, then of course I can just rewrite that in the following way: 4p upon rho t dt by dr and but with p equals rho mu upon kt, this is just the t cancels, and so what I get over here, of course, is minus gm upon r squared, and the solution to that is beautifully simple. It's just mu gm over 4kr, where k, of course, is Boltzmann's constant. Now, at this point, you might be saying to yourself, hey, that's weird. I'm telling you that the temperature doesn't depend on the opacity, even though the calculation depended on the opacity. And the answer to that puzzle is, of course, that the density depends strongly on opacity. The temperature doesn't, and the temperature doesn't because of the virial theorem. I could have derived this result a completely different way by using the virial theorem, which says the gravitational energy is minus 3 times the integral of PdV, plus the statement, which does come from radiative equilibrium, which is that P goes as T to the 4th. Okay, now, this result, put numbers in. So this is so beautifully simple that the numbers are straightforward, and so here's the answer. T is about 4,000 Kelvin times mass in Earth units, and of course inversely as the radius in Earth units. So this says that in a situation like this, at the base of the envelope, once I've reached 1 Earth mass, I have 4,000 Kelvin. And actually, realistic models also give numbers that are sort of like that. The density, of course, depends on the opacity. And if you work it out, the density is, I'm not going to use all these horrible constants, but anyway, I'll just write it down once. So, of course, the temperature goes like 1 upon r, the pressure goes like 1 upon r to the 4th, and the density goes like 1 upon r cubed. You can see that satisfies both radiative equilibrium and equation of ideal gas. This, by the way, is called the radiative zero solution. It's a well-known thing in the history of stellar models. Now, since rho goes as r cubed, 1 upon r cubed, when you calculate the mass of the atmosphere, which of course involves the integral of the density, r squared dr, you can see that it's logarithmically sensitive to the outer boundary. And a whole bunch of other stuff which is much more important. I only do this to get across a very, very important idea. For indeed, it turns out that this kind of situation is extremely insensitive to the conditions at infinity. And that's actually part of what is meant by the radiative zero solution. So it doesn't matter much where you are. It doesn't matter much, surprisingly enough, what the nebula is in terms of its temperature or density. It's logarithmically sensitive. So I can change the density of the nebula by 3 orders of magnitude. It doesn't change the results significantly. Very important. What does matter, at least in this simple model, is the opacity and the luminosity. Very important parameters because there they are, right here. And if I make the opacity low or the luminosity low, the density goes up. making the luminosity low is like building the planet more slowly. So if I play the game I mentioned earlier of asking when does the mass of the atmosphere approach the mass of the core, with the possibility of some kind of instability or whatever, I'll explain in a moment why it's not really an instability. If I play that game, then provided I'm willing to wait longer and the gas is still around, I can still build something at a lower mass. So in this concept of a critical mass, it, I hope, is clear to you that the conditions I have to satisfy so that the mass of the atmosphere approaches the mass of the core are going to depend on what I believe about opacity, and that is actually still true in the detailed models, even though this is not a constant anymore. And it's going to depend on how much time I'm willing to wait. If I'm willing to wait longer, then I can do this whole process of adding gas and getting up to the critical mass just by having a lower luminosity and waiting longer. In fact, that's a crucial part of the understanding of how this system works. Now, a side argument about opacity. It's a dirty problem, but I have to at least give you a feeling for the opacities.
Dave,
Yeah.
what about having a modified realistic model in which I will calculate the TDR according to an adiabatic temperature profile, but I will keep the luminosity calculated from radiation, and then I'll get the critical performance. So the temperature profile will be somewhat more realistic, but the cooling will be determined by radiation, but somewhat the physics of the atmosphere will be...
What you find if you try and play games like that is that you are unavoidably driven towards a layered model where part of it is convective and part of it is radiative. You can't, I mean, this is an attempt to treat the entire envelope all the way out to the Hill sphere in one simple picture, and actually that doesn't work out. The outer region is invariably radiative, and then typically for realistic opacities, convective, and sometimes even other radiative zones. But you're welcome to try. So let me just say a little bit about opacity. Oh, before I do that, I need to, so I'm not going to go through all the numbers, but let me just simply point out that if I assume that the luminosity goes like gm squared over r times tau, which will scale, so I've got m squared here, I've got an r here, which is like, say, mass to the 1/4, once I get up to things that are like 10 Earth masses, as I talked about yesterday. This will go something like mass to the 7/4 of a tau. If I put that into here, do the integral, and ask when do I reach the state where the atmospheric mass approaches the mass of the core, here's what I get. You have to trust me on this, it's messy. I get 10 Earth masses scaled to the characteristic time, to the 1,000,000 years, I've used 1 million here, to the minus 4/5. I think I have the minus sign right this time, Mars. And kappa upon kappa 0, so the opacity matters, to the 4/5, where kappa 0 is 1 centimeter squared per gram. This happens to be historically the number that was used in the classic calculations for this kind of model, more detailed, kitchen sink models that Pollack and Bodenheimer did way back, around about 1990. So this gives you a feeling for the numbers, but let me say a little bit about opacity.
Dave,
Yeah.
you have a question?
Yes.
So here you take the luminosity as only the luminosity of constructing the solid core.
Yeah, I will get to the atmosphere in a moment,
Okay.
but of course the model breaks down, but I can wave my hands elegantly.
So you have
Maybe.
some lower bound you can't go below, right?
Right, well, that's a very interesting thing for the following reason. When you do a calculation like this, you're assuming that the solid objects that you're adding to the body are that the energy released, the kinetic energy going into thermal energy, is available for radiation. That doesn't have to be true. I could, in principle, have a very hot core. And in some cases that might happen. I'm now drifting off into speculative things, but the question of the luminosity is a non-trivial one. And in the current models, Ravit knows about this, and I'm involved also with Peter Bodenheimer. Peter's still doing models like this. You have to worry about the latent heat. So if you throw in a rock, you might vaporize that rock completely. That's a storage of energy. And so that means that this number would actually be too big. So there are issues like that. It's not clear how important they are, but there are a lot of technical issues. Bless you. I hope that wasn't in response to what I said. Just to give you a feeling for opacities, a lot of you probably have no feeling at all for opacity. I mean, what the hell is 1 centimeter squared per gram? Where does that come from? I'm going to give you 2 examples so that you can just get a feeling for opacities. One of them is Jupiter itself right now. So here's Jupiter right now. And here I can invert the observations to get what the opacity is at optical depth unity from which the photons are currently escaping in the infrared. So how do I do it? I write dp by dr equals minus rho g. And I write d tau by dr. Tau is now, I hope it's always obvious whether tau is time or dimensionless, meaning optical depth. This is the definition. Kappa is the opacity. That's the definition of optical depth through a distance dr. And of course I can just divide these equations. dp by d tau equals g upon kappa, and so p at tau equals 1 is g upon kappa. And this, observationally, we know to be of order of bar, a little bit less. So this is of order 10 to the 6. It's actually more like 3 by 10 to the 5 dynes per square centimeter. So that's about a third of the pressure in this room. This thing is a few thousand. And so you can see the kappa is about 10 to the minus 2. And the units here are centimeters squared per gram. And actually, this is an interesting example. This opacity for Jupiter now comes from hydrogen, molecular hydrogen. And it's pressure induced, which means that it wouldn't be there unless you had significant pressure. It's actually proportional to pressure. So it just so happens that kappa is about 10 to the minus 2 when the pressure is about 1 bar. But if you go to 100 bars, it's 100 times larger, roughly. Depends on temperature. It's complicated, unfortunately. It's very complicated. But anyway, that will give you a feeling. This is actually of some relevance to this problem because there could be, in some models, a circumstance where you actually had to worry on, you had to use molecular hydrogen. Yeah?
Because solids have settled out from the tau equals 1 surface to lower depths. So why isn't it dominated by drains?
You're asking about Jupiter. Yeah. So in the case of Jupiter, what you have is that this is certainly well above the water clouds, and even it's roughly actually at about the ammonia cirrus level. I'm not sure what you're thinking about with particles, but at optical depth unity in Jupiter right now, the particle contribution is relatively small. You can imagine exoplanets where that's not going to be true. In fact, we know there are exoplanets where that's not true.
If you go into the interior.
But if you go into the interior, so you have a water cloud deck, but that's much deeper than this level. then you have droplets. But that's not going to be relevant to this calculation. There are people in this room who know a lot about this problem, but it's not going to be relevant to what I'm doing here. To make contact with what Pollock did in particular, Jim Pollock was an expert in this area. He knew all about opacities. Here's the other game that you can play. You can say, okay, let's have particles, and let's assume, this is not true if the particles are of order or smaller than the wavelength of the photons, but let's assume that it's just a geometric cross-section. So let's just do that. So rho kappa in that limit, so this is particles, suspended particles. Then of course, this is just like the standard problem of mean free path. I've got a bunch of particles, and I run a ray of light through the system. Is it going to hit the particles? And so that'll just be n times sigma, where this is the number density of the particles, and this is the cross-section. And of course, you can just write that. The number density is going to be the heavy element fraction times the actual density, heavy element mass fraction times the actual density, times pi r squared over 4/3 pi r cubed times, times rho zero. It's the mass of the particle. And so that model will give you kappa goes as F over rho r. And so with F we're 10 to the minus 2, say, and rho were 3 grams per cc, and the particles were, say, a few hundred microns, like 3 by 10 to the minus 3, then you would actually get 1. Now, I'm cheating. This is not actually what Pollock and company did it. They did it much more carefully than this. But I'm just doing this so that you get a general sense. I'm cheating because I can't really treat it as geometric optics for those particle sizes. All right. 20 minutes. Okay. So let's go back to my questions. And this is where I start waving my arms, as if I hadn't already. I hope you can see from what I told you that there's already some fuzziness with this idea. What has happened in the field is that people saw this calculation of 10 Earth masses, and then it got repeated by others with roughly similar numbers, and so this notion developed in the field without thinking that carefully about it, that yes, the number was 10 Earth masses. But I hope you can see that's a bit more complicated than that. Now, it's true that that's often actually what you get, but you should be wary of that number. Now, let me tell you, and this is where I start waving my arms, about how this really works. So this is how it works. You build your core of condensed stuff. You're aggregating the gas on top quasi-hydrostatically in the way I've described. And you approach the point where the mass of the atmosphere becomes a significant fraction of the mass of the planet. Now, here's the problem. If I'm adding a substantial amount of mass in the form of gas, I have to add that to my energy budget. And this is going to work back on the density. So if I ignored that, I would indeed get an instability. That is to say, I would find that there's a particular mass beyond which I can't get a hydrostatic solution, And I would say, as Mizuno did in 1980 or thereabouts, and I said it too, and I was wrong, that then you get some sort of hydrodynamic collapse. Because what we said, incorrectly, is that if there comes a point where hydrostatic equilibrium can no longer be satisfied, then the gas will rush in like gangbusters, and you will zip all the way to a giant planet overnight, 100 years, 1,000 years, depends on how quickly you can deliver the gas, which turns out to be not too big of a problem, actually. So, the whole business about Bondi radii in terms of the accretion radius and so forth, I'm not dealing with that here, but that turns out to be not the serious problem. And of course, we were wrong. Why were we wrong? Because it's a self-inconsistent argument. If you get to the point where you can't have hydrostatic equilibrium, there are two possibilities. One is that indeed you have some sort of instability, but the other is that the parameters that went into the hydrostatic equilibrium change with time, and they will. The luminosity will go up if I try to add too much gas. The planet will actually puff out. And so that will act back on the solution so that I can still maintain something that's quasi-hydrostatic. And so that's actually what happens in the classic models of Pollack and Bodenheimer, where what they do is, as a function of time, they accrete a core, and the details of this don't matter, but it might be 1,000,000 years. It doesn't actually matter that much. And then there's this long period where the mass slowly builds up, and then eventually it takes off. Now, why does it take off? It takes off because once I can reach a point where adding more mass allows the body to contract, then I can add gas over here. But this part, this crucial part here, which may be a few million years, is arising and can be understood qualitatively from the equations I wrote, simply because as I'm adding gas during this time, I have to get rid of the heat that is delivered by the gas that's being added. But you can see that if I were to lower this, that is, I only got to here rather than here, they assumed you got to 10 Earth masses, I could still actually do this, it's just that it would take longer. And if I change the opacity, I can do it earlier and a shorter time scale here. So I can change this time scale, I can do whatever I like here, I can get a variety of numbers. So this is tricky because of opacity and of course, because the fundamental physics was wrong, there isn't a critical mass in the sense that there's a number you can quote and beyond that you get an instability. That's not how it works. Nonetheless, something like 10 Earth masses often emerges. Now this is an interesting one. This is a classic example of scientists being too much swayed by looking at their own planetary system.
Maybe you have a question on the first one.
Yeah.
I just now started thinking. You said, well, at that pausing moment that you cannot accrete more gas into the atmosphere. But if you consider...
Well, you do, it's just that you do it slowly.
Yeah, very slowly, yes. But now I'm thinking, what if, you get solids which are infalling into the atmosphere,
Yes.
basically. That will increase the...
That will actually make it worse.
Yes, and basically...
Because it's adding luminosity, and that will actually try and make the planet puff up a bit.
Yes, it will puff up, and eventually will lose the lightest gases, and it will basically increase
Well...
in metallicity, in principle. Well, I'm just thinking, maybe would it be like that? Well, if those powder solids like pebbles would be like, enriched.
Well, this...
I hope you
So let me see if I can repeat the comment in question. You are concerned about the fact that if I'm adding solids, I'm changing the conditions in the envelope. Yeah. I didn't want to get into that. That's actually something I've worked on quite a lot because you'll notice right here molecular weight, and of course it also affects the opacity. So that's complicated. I'm sorry, but it's it's hard to come up with a better statement than it's complicated. But we're well aware of the problem. I will say this, that because vapor pressures are a very strong function of temperature, what often happens in the models is that you go rather quickly from a region where there's not much vaporized incoming planetesimals to a region where it's all vaporized. And that sort of becomes part of the core. And so then the core is sort of this supercritical thing, okay? I mentioned right at the beginning, you should, it's high density, but it sure as hell is, it doesn't have to be solid or liquid. It can actually be supercritical, but it's dense. I mean, remember the water, I mean, if I go up to 100 kilobars and high temperatures, I can give you water that's 1 gram per cc, but it won't look to you like water. It's like a very dense gas. So that can happen, and that becomes part of the core by rainout. That is, I bring in a planetesimal, it evaporates actually quite high up when it's fairly massive. Even the rock evaporates, so you get rock vapor. We're doing models like that right now. But it rains out. I mean, in other words, you supersaturate, and so it rains out. And maybe it becomes supercritical at greater depth. These are complicated things. I don't know whether Ravid's going to talk about.
Convective. I think we don't know.
It's actually, yes. And so the thermal state is also a bit mysterious. We don't actually quite understand yet how to do that right. It's a very interesting problem, but I'm running out of time. So, what about point number 2? This is very interesting. In the case of our solar system, a major reason for saying this had nothing to do with what I've talked about. It had to do with something else. It had to do with everybody's preconception that the surface density, the thing that Ruth talked about, had the property that once you got out to 5 AU, the amount of condensable was enough to make 10 Earth masses. Okay, now think carefully about the logic here. That means that if I can come up with a disk in another system, which for whatever reason has very high surface densities at 0.1 AU, I'm not sure you can do this, but if you can, that's perfectly fine. Because the model, as I described it, is not sensitive to the conditions of the nebula, except in the trivial sense of having enough stuff. Didn't matter what the temperature was. You can make, because the envelope is many, many thousands of degrees. In fact, tens of thousands of degrees. It doesn't matter if the nebula is 1,000. I can make a giant planet with a nebula at 1,000 Kelvin. It's not a problem, provided I have enough stuff. Yeah.
Yeah, speaking, I mean, it's not only about, I mentioned it last time as well, when Ruth mentioned it. You could also have like a lower surface density, even lower as the MMSM, and you could still grow like more mass just because of the variable accretion rate. If you have like higher.
That's 0.3.
Okay.
Good. Okay, so let me, yes.
But once you are close in to the star, does it cause problems with the microphysics of how things stick together and form this?
That's somebody else's story. Okay, maybe it does, but somebody else should talk about that if we want to address this seriously. It's not clear to me that that's the problem because, of course, people want to use gravitational instabilities, two-stream instabilities, to make planetesimals. So it's not clear how much the sticking matters. If you were at the evaporation front for the rock, that's really hot. But I would say you could even make a giant planet there, provided you've got enough stuff. Now remember, the kind of disk that Ruth talked about, the minimum mass solar nebula, by definition, okay, it's a circular argument, by definition it doesn't have enough stuff. So of course you didn't make a giant planet at Earth radius. So it's kind of a trivial observation. By the way, there are calculations now trying to form giant planets at small hours, paper by Konstantin Batygin and Peter Bodenheimer and Greg Laughlin. I think it may even be published. I'm not sure.
Dave, it might be worth mentioning that there's another argument that has been made that also doesn't stand up, but it's worth mentioning that at small distances, planetesimal accretion rates you might expect to be high enough that you're always keeping your envelope so hot that you can the density doesn't substantially increase toward the surface, and that's why you can't get
Maybe,
a mass.
yeah.
So this is an argument that was,
Yeah.
for example, around Raffikoff's work.
I-
That also doesn't hold up because you need very high accretion rates.
Yeah, I actually am not advocating that the exoplanet, giant planets, form close in. That's not what I'm doing here. I'm just trying to get you to realize that we had a prejudice that may not be as well founded as you thought.
I understood your point, and that's just trying to add the second part that sometimes people quote.
Sorry?
No, I understood and agree with your point.
Yeah.
I was trying to add there's a second argument. That
Yeah.
it's the same property.
Yes. And this gets to your comment. Remember what I said in the context of this calculation. If I'm willing to wait and there is still gas around, then I can still add gas because the hydrostatic equilibrium solution has this property that as the luminosity declines, the density goes up. As the luminosity declines, the density goes up. So if I have this embryo sitting out there and you're moving the nebula away, but you're not going down to zero density, then the process will still work. Now, of course, you can't go to ridiculously low densities because then there's another piece of physics, which is how rapidly you encounter gas. These bodies, of course, are moving at a different velocity from the nebula. I didn't go into that, 100 meters per second or whatever. So there's a whole bunch of other physics, which I haven't talked about, which will come into play when you start going to very low densities. Now, you saw earlier in the school, I forget who showed it, a plot, maybe Dave Charbonneau, I'm not sure. Somebody showed a plot of the density as a function of time, and it was fitted to an exponential. Data don't require an exponential, but if it were an exponential, you might have to go out to many, many e-folding times. E-folding time in that fit was 2.5 million years. You might have to go out to many e-folding times before the density in the nebula is so low that this process I'm talking about wouldn't work and you wouldn't keep accreting the gas. But you could imagine in principle, depending on your model for the physics of how the nebula is removed, you could imagine a scenario where you keep accreting gas and so you build up more of an atmosphere. And so for that reason, when we think about the puffy planets, not so much the giant planets perhaps, because the last stage, of course, does require a lot of gas around. But if you think about the puffy planets, maybe you could still add on 0.1% by mass, which is all you need. 0.1% by mass for a body that's a couple of Earth masses to make it look substantially bigger. And you might be able to do that at 5 million years, maybe even 10 million years. I don't know. Now, of course, there are models, like Hollenbach's models, for getting rid of the nebula, which won't predict an exponential decay. They will basically be more like a cutoff. But then, of course, you have to think through how the disk evolves, the things that Ruth talked about. I mean, that is a very interesting question. What really happens? Everybody says, oh, the nebula goes away at 3 million years, but what does that really mean? When is it really clean the way our solar system is? It's a very interesting question. I think I will stop there and a couple of minutes for questions.
Questions?
Yeah.
I have a question about this M versus T plot.
Yeah.
So when you finally run away, the runaway there is not hydrodynamical, right? The luminosity
Yeah.
Eclipses, right?
Yes,
So.
although because the mass of the envelope is at it may depend on the details of the model, but in the particular case of the kind of model that Pollack and Bodenheimer did, what's happening at this point is that the mass of the atmosphere is actually about the mass of the core. That's not true over here. Over here it's only a few percent. So it builds up from a few percent to 100%. At that point, little g starts to be dominated by the mass of gas that's added, and that can do the work, the gravitational work, to allow the accumulation of more material without the thing blowing up in your face. Whereas over here, the problem is that you still have a rather small contribution to little g from the gas that's added, and so the gas tends to spill out over the Hill sphere. Okay.
Like that criteria requires discontinuity of the densities between nebula and somewhere accrete in the giant planets.
Which
The runaway point.
you get a shock. Is that what you mean? Yes, you do get a shock. In his models, in Peter's models, you actually do develop a shock. So you have very low density outside, then you have a shock. You know, there's a whole literature in this field that I haven't talked about at all, which, you know, puts in rotation and tries to calculate streamlines of stuff coming in, Lubel's work and other people's work, and of course they get shock fronts, and that's where the jumps are occurring between them. And obviously none of my story has any of that.
Any more questions? Let us thank Jacob again. Lunch. Lunch would be at the place that it was yesterday, that Bretter, where next to the Einstein telescope. Have you visited the Einstein telescope?
Yes.
Okay. For the evening today, the party starts at 8. I suggest you can be there even a little bit earlier. I think they will let us in from 7:30. What we plan for the evening is some tour of the museum. There will be some guides there that will show specific exhibits. We'll have dinner. We'll have talent, what do you call it? Talent show by you.
Talent show, question mark.
And if the lecturers will stand up to it, maybe they can demonstrate their talents, I don't know. And then there'll be, there'll be drinks the whole time. And we'll have a dancing party after the drinks. During, after, and after the whole thing there will be a dancing party, and we'll end around midnight or slightly later. So yes, we'll meet again here after lunch at 2.
And party as well. Where is the party?
Oh, the party is at the Science Museum. Isn't there a map in your notes with the Science Museum? Okay. If you come to the campus,